we need to do right now is we're going to rationalize the denominator of a fraction. That's what they say when you cannot have a radical in the denominator. It's kind of like we don't leave 0 in the denominator of a fraction. It's not possible. Or we don't leave something unsimplified as our final answer. Later on, you're going to find that most of us, when we get higher levels of math, are going to leave the radical just because it gets applied somewhere else. For right now, with our final answer, we want to get it out of the denominator. Rationalizing means we want to take this fraction. We do not want to change its value. The only way to not change its value is to multiply by 1. We want this bottom number to actually be able to take a square root. The closest perfect square to the number 2 is the number 4. So if I go through my list, 4, 9, 16, 25, 36, the closest one to 2 is the number 4. The only way to get 4 is to multiply 2 by 2. I want to multiply by this special number 1 because 1 times anything won't change the value. I just want to change the way it looks. When I multiply straight across, I end up with 5 radical 2 over, now this is the square root of 4. I know that the square root of 4 does come out to be 2, so 5 radical 2 over 2. There is nothing that I can do. If I cover that up, 5 over 2 can't be reduced. Don't change it to 2.5. Leave it as 5 over 2. So this is our final answer. This value here, 5 over radical 2, is identical to 5 radical 2 over 2. If I plugged both of these in my calculator, did the division and all the work, this and this will have the exact same decimal. So both of these are the same value. We just don't see a square root in the denominator. So if I look at a different type of problem, this idea of our radical now in the denominator is a much bigger number, 12. But I want to ask myself, in order to rationalize, I again want to multiply by a special number 1. Sure, it would be easy to multiply by radical 12 over radical 12. We know that's going to turn out to be a perfect square for sure, because 12 times 12 is obviously a perfect square. But the issue would be I've got too much simplifying then that I might need to do. So my suggestion is find the closest perfect square. So I go through my list. We don't want to multiply by a fraction, so we don't want to divide 12. We always want to multiply and make it bigger. So 12 times 2 gets me 24, but 12 times 3 gets me 36, and 36 is a perfect square. So I'm going to multiply top and bottom by the square root of 3. Notice these numbers don't match, but when I do multiply them together, I end up with the square root of 36. Just like here, when I multiplied them together, I got the square root of 4. So when I multiply straight across, I also get 8 radical 3. Now in my denominator, I'm going to end up with 6 because the square root of 36 is 6. If I get rid of that for just right now and you concentrate on like terms, 8 over 6 we are able to reduce. It reduces by 2. So 2 goes into 8 4 times, 2 goes into 6 3 times, which is now why you see 4 over 3, but don't forget that we're still multiplying in that radical 3. This value and this look very different, but if you plug them into your calculator, you would get the exact same decimal. This is the rationalized version of that fraction. Let's take a look at another example. Instead of looking at any number on the bottom, let's concentrate on an example where we have 5 over the square root of 7. This number, very much like our number 2 from the other example, those are prime numbers. The nice part about prime numbers, you only have one option. You always have to multiply by the same number. Radical 7 over radical 7. When you multiply straight across, 5 radical 7 over the square root of 49, which automatically gets you right back to the number 7. And what you should start to see is a pattern. Notice here, we started with 5 over radical 2, and now we have 5 radical 2 over 2. Here we started with 5 over radical 7, and we ended up with 5 radical 7 over 7. In the next one, if I wrote down another problem, 3 over radical 11. You should see a pattern. The only option is the radical 11 over the radical 11, 3 radical 11 over 11. Pattern exists because this is a prime number. However, if it is not a prime number, find the closest perfect square. So let's look at negative 4 over the square root of 6. 6 times 2 is 12, not a perfect square. 6 times 3 is 18, not a perfect square. 6 times 4 is 24, not a perfect square. 6 times 5 is 30, not a perfect square. 6 times 6, so even though 6 is not a prime number, as I go through my list, that is my only option. And when I multiply straight across, 4 radical 6 over the square root of 36 is negative 4 radical 6 over 6. Like terms can reduce, and we're left with negative 2 over 3, but that radical 6 is still there. Make sure when you are finished looking at this video that you go back, go into the handout folder, and under the January 26th through 30th notes, you'll find that we did rationalizing the denominator of a fraction on 2 or 3 different slides. Make sure you get those examples with the notes as well.